All right, so here we are, back in the land of trigonometry, chapter 6, moving on, charging forward, bravely forth, hiding notifications. Section 6.3, we're just going to keep studying these trigonometric functions, sine, cosine, tangent, cosecant, cotangent, secant, and their various properties. So specifically, we want to learn about domain and range. They have a property called a period, which we will investigate. Okay. In different quadrants, the functions have different signs, SIGN meaning positive versus negative. And we can find the value of trigonometric functions using some fundamental identities that we'll introduce. We also want to be able to find exact values of trigonometric functions given one. So for example, and a quadrant. So for example, a problem will say like, you have a quadrant 2 angle and the sine of the angle is 1/4, find everything else. Okay, and even odd properties. So let's get into it. So just remember, here is how these functions are defined. You take your unit circle, meaning the radius is 1 and the center is at 0, 0. You start by going in the positive x direction. You measure in the counterclockwise direction. You mark off your angle of theta. That points to a specific point on the circle with coordinates x, y. And by definition, the x coordinate is the cosine of the angle. The y coordinate is the sine. The tangent is the y over the x, which you can also write as sine theta over cos theta. The cosecant is 1 over y, which you can write as 1 over sine theta. The secant is 1 over x, which is also 1 over cos theta. The cotangent is x over y, which you can also consider to be cosine of theta over the sine of theta. Okay? So this is all stuff we introduced in the last section. So what's the domain of sine and cosine? All real numbers. Because in that unit circle, starting from this direction, I can measure positive angles. And remember, I can keep going. So there's no limit on how many times I can go around. So I can take the sine and cosine of an angle from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi to 4 pi to 6 pi to 8 pi to 10 pi, etc., etc., etc. I can keep going. And I can also take the sine and cosine of negative angles just by going in the opposite direction. So again, unit circle, terrible drawing, but it's the best I can do, and I wish I weren't kidding. You can take the sine and cosine of negative pi over 2, negative pi, negative 2 pi, negative 4 pi, just by going around and around and around in the negative direction. So there is literally no angle that you cannot take the sine and cosine of. If you are used to working with triangle-based trigonometry, this doesn't quite make sense. Okay? And I've hesitated to mention it, but a lot of people are used to doing it. The triangle version of sine and cosine, the angle can only be between 0 and 90 degrees, otherwise it doesn't make any sense. But in our circular-based definition, you can take the sine and cosine of any angle, positive, negative, enormous, whatever. Okay? So the domain of both of these basic trig functions, sine and cosine, is all real numbers. Tangent, however, remember the tangent of theta is the y-coordinate over the x-coordinate. So we need this x-coordinate to not be 0. In other words, we need the cosine of the angle to not be 0. So in our unit circle, up at the top here, a small diagram, x equals 0 is exactly the y-axis. So what angles will have a cosine whose x-coordinate is 0? 90 degrees, aka pi over 2. Or 270 degrees, aka 3 pi over 2, or 5 pi over 2. Notice once I have hit the vertical line once, another pi will do it again, another pi will do it again. So a single pi over 2 plus any quantity of pi's is what will cause the cosine to be 0. And if you give this a common denominator, you'll end up with 2k plus 1 over 2 times pi. So the domain of tangent is everything except where cosine is 0. Cosine is 0 at an odd number over 2 times pi, which is what is said in the second thing here. The domain of the tangent function is all real numbers except odd multiples of pi over 2. Okay. That also applies to the secant function. Okay, because the secant function is just 1 over cosine. So again, your only problem is, what if the cosine is 0? That happens at odd numbers times pi over 2. So the domain of tangent and secant is everything except an odd number times pi over 2. For very similar reasons, the domain of cotangent and the domain of secant, both of these involve division by y, either x over y for cotangent or 1 over y for secant. Y equals 0 is the horizontal axis. So what angles will give me points either here or here? Well, an angle of 0, because that's where I start, or pi, or 2 pi, or 3 pi, or 4 pi, or negative pi, or negative 2 pi. So basically any multiple of pi. Okay. So the domain of cotangent and secant is all numbers except, and this is actually incorrect, it's just any integer multiple of pi. Okay. Pi also not in the domain of secant or cotangent because the y-coordinate is 0. So any odd multiple of pi over 2 will cause the x-coordinate to be 0. Any multiple at all of pi will cause the y-coordinate to be 0. Now, as far as range goes, so in the unit circle, okay, remember, as you rotate around, your x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. But let's take a look at the sine, the y-coordinate. The absolute biggest the y-coordinate can be is at this top point, which has a y-coordinate of 1. So the sine of any angle cannot ever be bigger than 1 because the y-coordinate as I spin around never gets above that point. Similarly, the lowest it ever gets is this point, which is at negative 1. So as you spin around the circle, the sine of any angle is trapped between positive 1 and negative 1. It starts at 0, it's increasing, it gets up to the highest value of 1. Now as I keep rotating, it starts decreasing. The y value is decreasing. Now it's 0, now it's down to negative 1. But now it's going to start increasing back towards 0, and it's going to start repeating that pattern, which is a phenomenon we'll see in a minute. But basically, the y-coordinate is trapped between 1 and negative 1, which means the sine of any angle is between 1 and negative 1. But the x-coordinate is also trapped. Okay, so I'll switch colors quickly. So if I draw the x-coordinate, the biggest the x-coordinate can be is here, and that's at x equals 1, and the smallest the x-coordinate can be is here, and that's at x equals minus 1. So the cosine, or the x-coordinate, also just goes between plus or minus 1, but never outside that. So sine and cosine are trapped in between 1 and negative 1. And now, this actually tells me that cosecant, which is 1 over sine, okay, if sine of theta is negative, then 1 over sine of theta is negative. Okay? But if sine of theta is negative, it can't be any less than negative 1. And this tells me that the sine of theta is bigger than, is less than minus 1, in fact, because I reciprocate this. So if sine of theta is very small, 1 over it is very big, but negative if sine was negative. So cosecant, if sine is negative, must be negative, but the biggest it can be is negative 1. If the sine is positive, then 1 over that is also positive, but very big. Okay, so cosecant can never be in between 1 and negative 1. It must be outside them. Similarly, secant, for the same reasons, since cosine is in between 1 and negative 1, 1 over them is outside 1 and negative 1. Tangent can actually be anything, and cotangent can also be anything. So let me throw a picture of the unit circle up here to try to at least sort of justify that. Here's our unit circle. And the tangent of theta is the ratio of the y to x coordinates. So imagine I have very, very small angles here. Okay? So y is small, and x is close to 1. Then the tangent of theta is small, but positive. If I took angles down here, y is small, but now it's negative. X is still positive and close to 1. Okay, x coordinates over here are still positive. So tangent can also be small and negative. But now let's imagine the angle getting really close to this. Okay? So now y is close to 1, and x is small and positive. Now what I have is I have a number close to 1 divided by something very small. So tangent can also be very big and positive. But if I did the same thing down here, now y is close to -1, and x is small and positive, so I can also have very big negative numbers when I take this ratio. So tangent can actually be anything. It's not bounded at all. Cotangent for similar reasons. So in summary, the sine function has domain all real numbers, but the range is between plus or minus 1, which it can equal. It can include plus or minus 1. The cosine function has domain all real numbers, and its range is all real numbers from plus or minus 1, including those endpoints. The tangent function, the domain is all real numbers except where the cosine function is 0, because that would be a denominator, and that's odd multiples of pi over 2. So everything except odd multiples of pi over 2, but the range is all real numbers. Okay, cosecant, and I'm going to skip down to secant, because it has the same domain restriction. You don't want the denominator cosine to be 0. So that's everything except odd multiples of pi over 2. Secant does have a different range. It's everything outside of plus or minus 1. Cosecant also has the range everything outside plus or minus 1, but its domain is everything except whole numbers times pi. Cotangent has that same domain, except whole numbers times pi, but now its range is all real numbers. And this isn't so much about memorizing. Most of this you'll pick up. The really important ones are these first two rows. Sine and cosine, the domain is everything, but the range is trapped from plus or minus 1. Okay. Otherwise, everything else involves a quotient. Tangent is sine over cosine, cosecant is 1 over cosine, etc. So the domain restriction just comes from try not to divide by 0. So one thing to observe is that suppose I have marked off this point by doing an angle of theta. So y is the sine of theta. But now suppose you do the same angle theta, but then you go around an extra 2 pi. So my angle is now theta plus 2 pi. I'm at the same point, so this is also the y-coordinate associated to the angle of theta plus 2 pi. But what if I went around again? This would be the same as the sine of theta plus 4 pi, or the sine of theta plus 6. If I just tag on an extra rotation, I do not change my y-coordinate. So the sine of theta plus any multiple of 2 pi doesn't change, because you're really pointing to the same place on the circle. But since it's the same place, it also has the same x-coordinate, so the cosine also doesn't change. This is what's called periodicity. Whatever the sine function does, when I do a full rotation, it starts the same thing again. Okay? So a function is called periodic if it has exactly this property. If shifting the input by p repeats values, then it's called period. If p is the smallest number that does this, then that's called the fundamental period of the function. Basically, it's how long the function takes to repeat itself is called a period. And if that's the smallest amount of time that can cause that repetition, it's called the fundamental period. So the period of sine and cosine is 2 pi, and that's actually a fundamental period. Okay, so sine starts to repeat itself after you do 2 pi worth of rotation, and so does cosine. It's not immediately obvious that tangent actually starts repeating itself after pi. Cosecant and secant, because they are just 1 over sine and 1 over cosine respectively, since sine and cosine will repeat themselves after 2 pi, cosecant and secant will also repeat themselves after 2 pi. And cotangent is just 1 over tangent. So since tangent repeats itself after pi, so tangent. So why does tangent actually repeat itself in less time, half as much time as sine or cosine? So look at this unit circle. Okay, so the sine function is the y-coordinate of the point you're looking at. The cosine of theta is the x-coordinate, and the tangent of theta is the ratio y over x. So let's just look at the sine function, the y-coordinate. As I start marking off angles and rotating around, the y-coordinate starts at 0 and is now positive. The y-coordinate is now 1, and now it's decreasing. I haven't repeated anything because I was increasing and now I'm decreasing, and that's different. I've repeated values, but not overall behavior. Oops, go back. The sine function has now come down to 0. Then I keep going, and now it's negative. That's entirely new behavior, so I definitely haven't repeated anything. Now the sine function has come down to -1, and now it's coming back up. But observe, once I go all the way around, I'm going to start doing exactly the same thing. Increase towards 1, decrease towards 0, decrease to -1, and I just keep going around. Okay? So sine takes a full 2 pi rotation to start repeating itself, and so does cosine. What about tangent? It's the ratio y over x. So notice, in the first quadrant, y and x are both positive, which means the tangent is positive. In the second quadrant, y is positive, x is negative, which means tangent is negative. In the third quadrant, x and y are both negative, which means tangent is the ratio of a negative over a negative. Tangent is positive again. Here what we really see is that what happens here with positive values of x and y happens here with negative values of x and y. Individually, sine or cosine can tell the difference between a positive and a negative number. But tangent, if x and y are both negative, doesn't tell the difference. Okay? If y is equal to -2, that wouldn't happen, sorry. If y is equal to -1/2 and x is equal to -√3/2, I'll have the same tangent as if y was positive 1/2 and x was positive √3/2. Because they're both positive versus both negative, the ratio loses that information. So tangent actually starts repeating itself just after pi, because it has actually lost some information in the ratio there. Okay. So can you find the exact value of the following? We're going to use periodicity. So for example, for the first one, we'd say the sine of 17 pi over 4, that's a pi, sorry. The question is, the input is something plus a multiple of 2 pi, okay? But I want common denominators of 4, so instead of calling this 2 pi, I'm going to call this 8 pi over 4. I mean, it's still just 2 pi. But basically, I want to express 17 pi as a multiple of 8 with something left over. And so what we said, this is going to be the sine of a single pi over 4 plus 16 pi over 4. That's the multiple of 8 that I can make closest to 17. 16 pi over 4 is just 4 pi, which is just going around the circle twice. Going around the circle twice, it does not change your y coordinate. And what's the sine of, whoops, somehow this became a 2. What's the sine of pi over 4? We have a table, it's √2/2. So therefore, the sine of 17 pi over 4 is the same as the sine of pi over 4, which is √2/2. So we exploited periodicity by saying the input 17 pi over 4 was some number of complete rotations plus something else. So try to do the same thing for parts B and C. Whatever the inputs are, for cosine, the period is 2 pi, so you want to ask, how many 2 pi's can I do, and then what's left over? But for tangent, the period is actually just pi, so ask how many pi's can I do, and then what's left over. So pause here and work those out. Okay, so A, we already did. Okay, it's just pi over 4 with 2 full rotations added onto it. So that's just √2/2. Let's take a look at part B. 5 pi is just go around the circle twice and then an extra pi. So it's pi plus full rotations, which is the same thing as having just done an angle of pi, and the cosine of pi is -1. The tangent period is only pi, so 5 pi over 4 is a full pi and then an extra pi over 4. So the tangent of 5 pi over 4 will be the same as the tangent of pi over 4, and we can look up our chart from the previous section and see that that's just 1. Okay? So we'll actually stop this video here. It wasn't a terribly long one. Looking ahead, there were some other places I wanted to introduce breaks. The next video is also going to be pretty short. We're going to look at some quadrantal properties. What do sine and cosecant, etc., do in the various quadrants?